gamma shows E as some label. So given this, and I know that, and I know we have a sigma here, right? I evaluate E under sigma, that will give me a B. So I want to specify an interference about E. How should I be specifying this? I had an example on slide yesterday thinking about 2 exclusions. Anybody else have thoughts? Think about it, yeah.
Can you write slightly bigger?
Oh, where did you get that? So you write the pattern here, L, the evaluation will have this, right? That's what I have. How do I write a non-interference definition for E? Yeah.
So to recall, non-interference says that for any starting initial inputs, if the public are the same, but you change the secret, the final value is also the same.
Yeah.
So here, what I believe you need to say is that for 2 different sigmas, you keep the public one the same, and any security that is larger than L, you change that, and you still get the same B.
Yeah, so basically, here the input are sigmas, right? Somehow, let's say that I have a lemma for Ni for E. So, is it large enough? This is not so many symbols. So somehow, obviously I know this condition. Somehow I need to find 2 sigmas, sigma 1, sigma 2, so that, as you were saying, they agree on the public variables, but differ in secret, right? So let's say that, let's be a little bit more general. Let's go beyond this L and H. I have a general lattice. Now, when I define attacker, typically attacker is defined with a label. So let's say that, let's call the attacker label LA. So this LA can be any label on lattice, right? Because I can say the attacker have, if I have a L low, medium, high, the attacker can be low, can be medium, so on and so forth. So somehow what I want to say is that these 2 somehow agree on something under the observation of this attacker label, right? We're almost there, but this label of the variable actually comes from gamma, right? So in some sense, typically what we write is where, let's see what's better with write. Maybe it's easier to say that under gamma, sigma 1 and sigma 2 are equivalent for the attacker under label L2, right? So let's say that somehow we already defined this because you can guess what this might look like. So if I have this, right, so to begin with, for this E, I know this E type check under L, right? So basically now I'm going to evaluate E under sigma 1, that will give me V1. Only V1. Then I evaluate E under the second second thing. So I can't do imply here. So what's the symbol I should be writing here? So there's an L, right? This is the expressions label. This is the attacker's label. So it depends, right? If the attacker can see this expression, I should write equal. If this is a high expression, the attacker shouldn't see it and shouldn't be equal, right? So basically, since I already used this symbol for stores, so you can think that I actually have some of equivalence of value 2 at a label L under an attacker, right? So this looks like non-interference, right? So you have well-typed expression, and I have 2 stores. They're implicitly well-typed under this gamma, right? If here in gamma x is low, then these 2 stores would agree. I'll write this out later. And then that if that's the case, that implies that if I evaluate under 1, this should be equivalent given label L under attacker's observation LA, right? So we have to, when you do a general lattice, you have to prioritize over these labels all the time, right? So now I can actually be a little more specific in spelling out these definitions, right? But this definition seems to look okay, right? Okay, this. One thing I'm not dealing with is termination, because my expression is so simple. Right? They're only binary operations and variables. So this got to terminate. So writing this is pretty straightforward. If you think about termination of commands with a while loop, we have to be a little bit more careful. Right. Okay, so this is our NI for E. This is the definition. Now I have to do a little bit more definition. Right, I have to define more. Definition. I want to define the value first, right? So I want to define what does it mean for a value v1 equivalent to v2 at a level, right? So, and to do this definition. Box this one here, I guess. How do I do this? I'm going to use derivation rules here. What are the cases I should be considering? There are two cases. Yeah, I need to compare LA and L, right? I decide whether the attacker can see this or not, right? So if L is lower than LA, that means that, so here, these two would really have to equal, right? So here, basically I can say that V equivalent to V at L, right? So I can also say V1 equivalent, V1 equal to V2, but I just put V here to be simple. Then for the other one, I just said any V1, V2 will be low equivalent at L if L is not lower, not lower equal to LA. Right? Right, so these are two cases, yeah? Any questions? All right, so with this, it's not hard for me to define this one now, right? Because in the end, I can compare values of the store. Right? Maybe I'll give you a couple minutes, have you guys write down this definition. Let me see my real estate. What's the best way to not write? Yeah, so basically, I would like you guys to define gamma shows sigma 1 equivalent to sigma 2 under LA. You can use this definition. Yeah, so spend a couple minutes, write it out. Again, there are two cases, maybe three cases for a base case. And now I'll write it out. Base case, the simplest one. Yeah.
I actually just have some syntax questions.
Yeah.
So L subscript A, how do we read that?
It's a attacker label. So for here, actually, I'll quantify over all three variables. So for any attacker label LA, for any L, E is type checked under. So this is the statement. It works for every A because for every L, every LA because this is parameterized over the L's, right? Because the attacker can be at different levels, right? Yeah.
So what is the difference between the two expressions on the bottom?
So these are two expressions. Maybe I should actually write this better. Well, 1 equal to 2. I was too lazy. Yeah, I didn't put the subscript. Yeah. Yeah, so what's the base case? The simplest base case. When you have sigma, what's the base case? Yeah, so anti-sigma is always equivalent, right? Gamma shows, I have to be a little smaller because, don't worry about this then. This is simple. Now, if I go to the, to figure out what's best to do the real estate here, maybe I should go to the right and see how it goes later on. So now we go to the inductive case where I have sigma 1 on one side, then I have x mapped to some value on one side, and then I have sigma 2 with x mapped to v2 on this side. This is equivalent to LA. So obviously the inductive case is just, okay, I'm going to look at smaller ones, right? LA and L2. What do I do here? So somehow I want to use that relation. What's missing for that relation? Yeah.
The V1 is equivalent to V2.
Yeah, so what's missing is this L. You need to dig out this L, right? So basically V1 needs to be equivalent to V2 at the type of X. Right? And look up this L. Yeah. Any questions? So that's the store equivalence that we're defining here. So in this here, where I force the store to be having the exact same set of variables. Yeah.
I have a question about comparing labels.
Yeah.
If we're talking about general lattices, is it a partial ordering?
Yes, partial order. Yes. So the letters have the L, the security letters typically. So different paper require different properties. On some ask distributed whatever drawing letters, etc., etc. But the basic thing is anti-letter relation. So basically, this L is whatever set of label you have, right? You can be H and L, so on and so forth, right? Then you have a less than relation between these labels. So yeah, so L is a set of labels, and then the less than relation is flow two. That's the only two things we need. That's a partial order, yes. And it is reflexive, yes. So L is always lower equal to itself.
Maybe it's a dumb question then. So we're comparing the label for E and the label for the attacker. Are they necessarily comparable?
Oh, if they're not comparable, you fall into this case. Yes, it's not, right? I'm not saying this is higher. I'm saying if you're not lower, because you can have letters like this. So you can have letters like this, right? You have bottom, you have top, then you have something else on the side. Then if I look at these 2 points, they're not comparable. The information still shouldn't flow between these two. Yeah.
For the right sign on the top of the sequence, the rule there for storage, the inductive rule for storage equivalence.
Yeah.
Is there supposed to be a gamma, like a context for the value equivalence?
So the value care about the values label.
Okay.
So I actually looked it up here already, right? So I don't need the whole gamma. I just need to know what X is labeled at. Yeah. All right, questions? More questions? Okay, so now we can actually do this proof, right? There are only 3 cases. Actually, the unary is just by, okay. When I prove this, how do I prove it? There's only typically 90% time give me one answer for any PL proof. Yes, I prove by induction. Induction over what? You can do over typing rule, you can over the, you should do it, with subtyping, we should do it over the typing rule. If there's no subtyping, you can do it over the structure of the expression itself, right? With subtyping, if you do the structure, you have to prove another lemma for the typing, for the subtyping. If you do induction over the typing rule, then subtyping is covered also. Right? I'm going to skip proving this because this is kind of sort of the simpler one. Maybe if you want to try a case at home, you try the binary operation or you combine two operations. Right. All right, so the more fun one would be the command side of things. Right, so now I can write out the command, the operation semantics for command. I actually use that part of the board. So I can prove on the top board. Maybe. More space. this together. These are only questions. So I actually want to evaluate sigma with command, right? So I'm going to use something. Eventually, I'll talk about trace semantics. So I'm going to write a semantic in a style that's actually easier to give me the entire flat trace. Easier to do that. So for me to do that, let's see. Let's not waste space. Well, it's fine over here. Not to waste space. So typically we care about the command. Mostly the annoying thing to deal with is wait, did I put sequencing? I forgot to put sequencing in language. We should add sequencing on the slide, but yeah. So typically dealing with execution, this sequencing is annoying. You can either do the congruence rule where you evaluate C1 first, and then whatever C1 you evaluate to, then you evaluate to the result. It doesn't give you necessarily a flat trace easily. So to do this one, another way to do this is to define an execution stack or a context stack. So the execution context E, bigger. I think I've seen this in your lambda calculus also. It can be a whole, or it can be a whole with another command, right? So this is, when you start execution, we always start with a whole, so easier for me to know when it terminates. When I deal with the semicolon, when I evaluate C1, I'm going to remember that I still need to execute the next command, but currently this whole is the one C1 is executing, right? So that's what I'm going to do. Because I can have sequences, keep sequencing, right? So I can have a stack of these. So therefore, I'm going to have a stack of context, right? So these are basically either empty, you have an empty stack, or you have E on top of the stack, right? So that's what I'm going to do, so that I can straighten out the traces. Okay. Let's see what's interesting. I'm going to write the sequencing rule. That's actually might be the, because assignment's obvious. I'm just going to skip that. So if I have sigma with a stack with C1 semicolon C2, maybe I'll write this way. Not go too long. Yeah, let's try this way. See if I can save space. So this one evaluate to, I'm going to save the context, C2 on top of S, and then I evaluate C2. Sorry, C1. Right. So this gives me a flat trace. Yeah. Okay. So that's one. That's a sequencing rule. Just because this exercise is stack, so I'm going to use that one. And then for me to pop this, the matching rule is like call return. If you think about this, if I have something on top of, I have a hole with C2 on top of the stack, and then I'm evaluating whatever I have. I have only two, not C update. So skip, typically when you finish executing something, you go to skip, right? This is indicating whatever you were trying to run now is over. So this goes to sigma. Now I can top the stack, right? And I continue to execute. But these are a pair, essentially. Right? Okay, and then the other thing I want to write is if. Right up here, I have sigma, I have a stack, I have if E. So for this rule, okay, not too hard for me to get to the top, but let's write it on the bottom then. So basically, for me, I'm going to evaluate this condition, right? Under sigma, this will give me true or false. So I'm going to write the rule for true. So if this one actually returns, let's imagine I have true. Good enough. If this one evaluates true, then this whole thing goes to C1. Right? So that's my branching. Yeah. So typically, if I have a bar, I'll put it above the bar. now you can space the bar, so I'm using a red condition on both. So these are straightforward, right? Maybe I should write assignment. Assignments is trivial enough. Maybe I'll skip assignments. All right, so that's my semantic rules. Okay, now I'm ready to define the same for C. What do I want in terms of non-interference for command? Maybe you guys can think about this, how best to imitate the definition for C, for C in terms of E. Yeah, I'll take a minute break and you guys can talk to your neighbors and try to write something out to see what works. One more rule for termination. Basically, you finish everything and you got your, so you start running your program, start from box, right, from the empty hole. Once you finish everything, you just go to halt. You can add that rule. If that makes your life easier to specify the property. Yeah. So when initial state of the program is, if I see a program that I evaluate, this is my starting point, right? Right. So eventually, I'm going to get to this point. After I finish everything, the stack is hopped, I went back to the original stack and I just say I want to halt. This might make your life a little easier in terms of specification.
As an entry fee, you're saying the other things behind there that similarity, right?
Yeah, so we may not have defined enough similarity or equivalence. So you probably do, you may need to dream something out, maybe you don't. So yeah. So you can define end-to-end property, right? So when you do inductive proof, you probably by now figured out your high-level theorem or corollary look too clean. When you start doing inductive proof, you realize you need more things. But the top-level statement can be very clean. You may not need any additional statements. You might just, because I start here. This is where I start, this is where I end, right? So then you have your closure of steps. Give it a try. I think if you get it, it's more fun than if I should write it on board before you think about it. Any thoughts? We can just start copying this, but change E to C, right? Yeah, so obviously we want well typed, right? Otherwise, any random command won't work, right? So there we have gamma shows E has L. In our C type checking, what we have is, we have a PC, but typically you always start running your program in the lowest elements of your lattice. There's no reason why you want to write from high, so we can just start from bottom. Show the C, right? So we don't have anything else, just like, okay, you think of this, right? This is the typing we have, right? And then, because the starting configuration is this, right? So we do need to specify what, we're looking at 2 executions, so this is not different from what's going on there, right? So basically we have any 2, sigma 1, sigma 2, so everything here is universally quantified from this amount run, right, for all. If you want to formalize this in Coq, this will be for all, LA with sigma 2. This is the same as this one, right? So that one, I want to say 2 execution end up being the same. These are values, they're properly defined, right? So this doesn't apply here. We just need to change that a little bit, right? The equivalence of evaluating E is to, starting from my initial configuration, let's just use I, so that I don't have to write it twice. With this is the first execution. This is one of the executions. Multiple step goes to sigma I prime with a halt, right? This is my resulting memory, right? So here, the expression doesn't alter memory. I don't care about memory. I don't care about final value. For commands, the observation is the final memory for the attacker, right? So here, I is in 1, 2, right? So this is essentially defining 2 executions here. If that's the case, that implies sigma gamma shows sigma 1 prime equivalent to sigma 2 prime, right? So this is almost the same. I just translate what I have for E back to commands, right? So now I want to prove. How do I prove this? We can try induction, right? So basically you think about it on top. I'm going to call this sigma, so I'm going to write this out. On top you have like sigma 1, you have a trace like this, maybe, and on the bottom you have sigma 1 prime, and it goes to sigma m prime. Right? This is our final output. These are final output. I think those are final configuration. Yeah, at least yeah. So you have 2 traces. How do I do induction?
We start with the sigma empty C, or
The start is sigma empty C, right? So start with the program. Yeah, I can start with the program. Initially, these 2, I have the same program, there's different memory, right? So we induct over what? How tall we do induction? What can we induct over now? What are the things that exist that look like we can induct over? Yeah.
Probably induct over the program itself, right? You said the program is the same in both cases.
Yes.
So you may be able to prove that the same program might take like the same number of steps. Are the number of steps the same or not?
I'll ask you, would the program number the same or not?
I mean, if the program is the same, I guess the only way that they could differ is the inputs, right?
The input is different.
So the steps could be different. So there's no point in inducting on the number of steps. So I think it should be the program that we induct on.
Actually, induct over the number of steps is the right answer. So, but I have 2 numbers here, right? There's n steps, there's m steps, right? So when you have this, sometimes you can induct on 1. So typically you can actually have a pair that you do a, this is not dictionary order, but right? So if this one gets smaller, then it's smaller, or this one remains the same, this one gets smaller. That gives me a well-founded induction. If you use the prop, you have to program this yourself, but there is proper well-foundedness you can define to do this, right? You have defined the measure of how to do the decreasing, then you can do it this way, right? So basically, I'm trying to induct over this pair of the length of the first, second trace, because these are fairly symmetric. It doesn't really matter which one is first. So just by habit, I'll tell over the first. So that was now, right? So I start with the same. What are you imagining would happen in one step? What would you run into trouble? Somehow I'm missing something, right? Yeah.
We would run into trouble if the first one adds something to a sigma that the second one didn't have.
So we don't do allocation, luckily.
Okay.
Yeah, if you have if you have multiple references, we don't have, luckily that's not a problem. Yeah.
The statement is still weak because it assumes only for empty stacks, and you need to say it for all compatible.
Yeah, so I'm not, so this is a very clean statement. I only have sigma here. But in reality, as I'm expanding out here, I actually have different S's that I deal with, right? So in your mind, so this is actually called a weak simulation proof. So basically what we're saying that eventually these two match. You can think of these two traces kind of sort of simulate each other. So in simulation proof, what we start off is we kind of first start off related state. As we were moving along, we're keeping this relatedness as we step forward. However, we're not defining this relatedness yet. We only said one part of it is related. I omitted S, right? This is too weak. I need to actually be properly defining this state sigma related to S sigma when there's a generic S in my system, right? Yeah.
So does S in this case mean lowercase sigma?
This one, the stack,
The stack.
the big S, yeah, yeah. So, okay, so now we have defined this, right? Maybe I don't think I'm running out of time. So the other tricky part is if you think about, so now you point out S is a problem. I'll point out another problem is that if you think about as the two traces I'm going forward, right? At some point you're going to get to a situation where if you start with a low context, you have the same command for a while until you come to this point, right? You have if then else statement, else C2. On the bottom trace, you also have the same, right? So far so good. Things kind of look similar enough. But let's say that this is actually a high variable, right? Given the sigma we have, let's say this is just x. X is actually secret here. So when I evaluate under the equivalent store, so I have sigma 1 up here, I have sigma 2 up here, they're equivalent because this x is high. That means that in x, in 1, this x mapped to V1. Let's just make that image, sorry, be square, I mean, just a bit more. Here I have x